In this video, I'd like to talk about the math question of the day for February 1st, 2023. And this word problem is an optimization word problem from calculus. So to answer a question like this, you need to have a solid understanding of calculus and basically everything that comes before it, since these problems can be fairly tricky. You do need to have a wide range of mathematical knowledge to attempt these problems. But at this point, go ahead, pause the video, see if you can solve this on your own, and when you're ready, we can go through this together. Now, assuming that you have attempted this problem, we can start working through this together. And as always, if you have any suggestions for future questions of the day, feel free to leave a suggestion in the comments. Now, with these optimization problems, we should start by making a picture. But let's first just read through the question. We want to build a box whose base length is 6 times the base width, and the box will enclose 20 cubic inches. So this is the volume of the box. The cost of the material of the sides is $3 per square inch, and the cost of the top and bottom is $15 per square inch. Determine the dimensions of the box that will minimize the cost. And we know it's an optimization problem because we are finding a minimum, or we could be finding a maximum. But this is a clue that we need to use calculus once we figure out the equation for the cost, or I should say the function for the cost. But let's start by sketching out a picture of this. And we have a box. So let me quickly draw a box in. And keep in mind that these pictures don't have to be perfect. They don't have to be drawn to scale, but they will mainly help organize the problem. So even on these simpler problems where we just have a box rather than a more complicated figure, it is important to practice sketching these because that will help guide you in these problems. And we're told with this box that the base length is 6 times the base width. So if we say this is the length, let me use a different color, and this is the width, then the length is 6 times the width. And they don't mention it, but we do have the height of the box. We can just call that h. And we're told that the box will enclose 20 cubic inches, which, since we have cubic inches, this tells us we're looking at the volume of the box. Volume is 20 cubic inches. But remember, the volume of a box is essentially the length times by the width times by the height. So we have the length, which is 6w, multiplied by the width, which is w, multiplied by the height h. So we have this equation here, our constraint on the equation, or on this minimization problem. And we have 6w squared times h is 20 cubic inches. And then we need to consider the cost of the material. And it's different for the sides and the top and bottom. Now let me put in some dash marks here so that we have a full picture so that we can visualize all of the sides. And let's create our function for the cost. We know for the sides, we can start with that, it's $3 per square inch, and I'll leave off the units, but we can figure out our square inches by looking at the surface area. So we need to essentially add together the area of the 4 sides. Those are the right and the front sides, but we also have the back side and the left side. So if we add the surface area of all 4 of those sides and then multiply it by $3 per square inch, that will give us the cost of the sides. And the surface area here would be 6w times by h, but we have 2 of those since the front and the back will be the same. So we have twice 6w times by h, and then we have the left and right sides. And again, we have 2 of those. Now for the right side, we have w times h, and that would be the same for the left side. So we have twice w, let me rewrite that, multiplied by h. So this gives us the cost of the sides of the box, but now we need the cost of the top and bottom. We know that's $15 per square inch. So if we find the square inches of the top and the bottom, we just multiply that by 15. And for the top, it would be 6W times W, but it would be the same for the bottom, so we have twice that, twice 6W times by W. And at this point, we can simplify everything here so that we have the cost of this box here. We can just call that C, C for cost. Now, rewriting everything, this is 12 WH plus 2 WH. We can combine those. And over here, this would be 30 multiplied by 6, so that's 180 multiplied by W squared. And simplifying everything, this would be 14 WH, but we're multiplying that by 3. That's 30 plus 12, so we get 42 W times H plus 180 multiplied by W squared. Now we need to minimize this cost function here, but it has two variables, two independent variables. So we can simplify this by using our constraint here. We can solve for W or H and plug it into this cost function so that we can reduce this to a one independent variable function. And looking at these two variables, it looks like it'll be easier to solve for H so that we don't have to take a square root. And dividing each side by 6W squared, 20 over 6 reduces to 10 over 3, and then W squared is in the denominator. So we can solve for H, and everywhere we see an H, we can plug it in to our cost function. So let me just make a little bit of room here. And we can rewrite this cost function now, C, being equal to 42 times by W times by H, but H is 10 over 3W squared. We still have 180 W squared, and we can simplify this further. We have 3 going into 42 14 times, and then 14 times 10 would be 140. W over W squared would be 140 over W, but I'll write that as W to the minus 1 power. But if you want to rewrite this as 140 over W, that would be valid as well. And then this is plus 180 times by W squared. And the reason I wrote this as W to the minus 1 is that we need to take a derivative of this to minimize the function. Since remember that if we have some random function, to find its maximum or its minimum value, we need to consider the derivative. Since the derivative just tells us the slope of the tangent line at some point, we can look at the tangent line at, let's say, a maximum or a minimum value, and notice that the slope at those critical points is equal to 0. So for the minimum, we can say that the derivative, the rate of change of the function, which gives us the slope of the tangent line at that specific point, the derivative here would be equal to 0. So if we take the derivative of this cost function with respect to the width here, this variable w, then we can just set that equal to 0 and determine the critical points. So let's take the derivative of this cost function, and we're taking that with respect to the variable w. So we're using the power rule. We bring down the exponent and multiply. We get minus 140, and then we subtract the exponent by 1. We do the same here. We bring down the 2. This becomes 360 multiplied by w to the first power. And we could rewrite this as minus 140 over w squared plus 360 multiplied by w. And we can even combine this all into one fraction. If we multiply the top and bottom here of this term by w squared, then we get minus 140 plus 360 w cubed all over w squared. And again, we're going to set this equal to 0 so that we can find these critical points. And we can see that in this equation, w cannot be 0. W can't be negative either since we're talking about a physical width. So we can say that W has to be bigger than 0. And if we look at the numerator when this is equal to 0, we have the equation 360 multiplied by W cubed minus 140 equals 0. We can add 140 to the other side and simplify. Let's divide by 360. So we get 140 over 360, which we can just divide top and bottom by 10, so that we get 14 over 36. And W cubed, if we simplify this further, divide top and bottom by 2, we get 7 over 18. And we need to take a cube root of each side, so that we get the cube root of 7 over 18, which as a decimal is approximately 0.73, but it might be better to leave it as this irrational number. Now, this is the only critical point here, and we think it's probably the minimum, but to be sure, we need to consider the second derivative, or the second derivative test. So going back to this general function, remember for the second derivative that is looking at the rate of change of the derivative. And the derivative tells us the slope of the tangent line at a given point. So we're looking at how that slope is changing as the function changes. And notice for a maximum that this slope of the tangent line is getting smaller and smaller, or more towards the negatives, as we increase or move towards the right, as we increase our independent variable. So the second derivative is decreasing here for a maximum point, but for a minimum, notice that if we drew in tangent lines, that they're getting bigger and bigger as the function moves along. So for a minimum, the second derivative is a positive value. So let's consider our function here, this derivative, and we can take its second derivative so that we can see if it's always positive. And if that's the case, then this is in fact the correct answer. So we're taking that second derivative of the cost function with respect to the variable w, and we'll just use that power rule again. We'll bring down the minus 2. So the negatives cancel. We get 140 times 2, which is 280. And this is w to the minus 3 now. And then we bring down that variable 1, multiplied by 360, and then we get w to the 0, which is 1. So we just get 360 here. And rewriting this, we have 280 over w cubed plus 360. And we just need to remember that we determined w is always a positive number since it's a width and it can't equal 0. It is a physical length. So this fraction here, since w is positive, this fraction is always positive, and then we're adding a positive number to that. So the second derivative is always positive, which means that this w value of 7 over 18, and we take its cube root, this is in fact a minimizing value. We have the minimum here. Or I should say this value for w gives us the minimum cost of building this box. So let's go back up to our question and make sure we answer everything. Determine the dimensions of the box that will minimize the cost. We figured out w, that's the cube root of 7 over 18. So at this point, we just need to plug it in to figure out h. And the length would just be 6 times this, 6 multiplied by the cube root of 7 over 18. And lastly, to figure out that height, we just need to use this equation here. And our height would be 10 over 3 times by w squared. So we would have this cubed root of 7 over 18, and we're squaring all of that, which if we want, we can rewrite this as a fractional exponent. We have 10 over 3 multiplied by 7 over 18 raised to the 2/3 power. And if we want to compute everything as decimal, let me just paste in what the answers would look like. But these would be our three decimal solutions. But if you want, you can just leave these in their irrational form since each of these are approximations.